Okay, great to see everybody here tonight. Um, it's the weekend of August 9th, 10th. Where is the year going? And we're here with our conversations with Amy Edmondson's A Fuller Explanation. And, and if I'm hankering right, we're going to begin roughly um, on, gee, I thought my page was all ready to go. I think we're starting with isotropic vector matrix on page 143 is where I believe that we want to be. 510, maybe not. No. Gosh, we'll get the introductions going and I'll slowly come to the page. Well, there, I'll use my marker. 8 Yeah, I'm going to have to take a look at this. All right, good. So, Joe, how are you feeling tonight? And what do you anticipate getting out of the call in spite of my rambling here at the beginning?
No, I mean that rambling was actually it's great. And it's good to see everybody, and I'm feeling pretty good. And so yeah, I mean as far as kind of what I'm expecting to get out of tonight is just to build on the basic concept of when we started with multiplication by division, which we had discussed, and that I'm still starting to see some ideas emerge from that. Starting to understand patterns in nature and in recursive structures and things like that. So it's been really exciting in that regard. So I'm grateful for the synergetics being made accessible, so to speak, and then continue to make connections through what we're doing on our Wednesday calls. So in case, Lee, how are you feeling? And what would you like to take away from today?
I'm doing wonderfully. It's been a good day today. I've experienced some great things, and I was so excited last week with the design of the balls that were lined up, starting with 1, went to 2, went to 3, 4, and on. And that brought me back from the first time I was on, there it is, n2 minus n equals n minus 1, n over 2, I guess you have to say, equals the last row. And it was the first time I joined you all, and it was nice to see it again. And how are you feeling? And what would you like to take away from today?
Thank you, Hailey. Good to see you. Good to see everybody. Today I'm looking forward to delving deeper into that multiplication by division. I'm starting to tell people that it blows the mind to have that to even have that thought, to even understand that's how the world works. And grateful to have everybody here. And excited at the same time to see what's going to come out from today's meeting. Yeah. And Richard, is it Richard? No, Richard has gone. Joe has gone. Steve.
No, Richard hasn't gone yet.
Oh,
we were just chatting before the call. So
okay. So Richard, how do you feel, and what would you like to take away today?
I'm energized, and I'm on the cusp, or on, I said the virtual, not the literal, sort of evening of before I do a presentation to an indigenous group of social workers at my university, University of Calgary. And what I got started on is that I'm trying to find a substitute for the word self in self-determination. And I'm expecting some pushback on it. Although it comes out of a chapter that was just published and in a book with the general title of Pushing Boundaries. So pushing things to see if we can bring about change. So this is my push. So I blame my association with Fuller over the years for thinking about co instead of self. So who knows, maybe in the nature of our discussion and dialogue this evening, I'll get even a little bit more clarity in terms of how I want to push and how I want to aikido with the pushbackers. So, Steve, how are you feeling? What's your expectations for this evening?
Okay. Well, I'm feeling, I guess I'm feeling kind of tired. I was real disoriented here at the beginning because last week we started at vector equilibrium on page 171, but we never left the page. What we started doing was talking about the stacking and talking about the n squared minus n over 2 relationship formula. And we spent the whole time on that. I had completely forgotten about that. And so I very quickly checked my notes, and I'll just share with you what my notes said from last week. I'm going to go ahead and share screen because that'll be the easiest way to do this. So here's how I track the calls each week. So this was August 2nd or 3rd, and we just had a free flow discussion about triangular numbers. And I did a little chart after our call, referring to that graphic about computing the number of balls at the bottom of a two-dimensional array of closely packed spheres. So actually, then tonight we're going to leave off. We're going to start out where we left off the week prior, which is in chapter 10 on page 171. And let's see, there are a couple ways to get here to hear from there. Oh, I keep looking past it. So there we are right there. And yeah, how do I feel? Well, I really, it seems to me that more I contemplate it, I have to divide in order to multiply. I'm not sure how, I'm not sure how I came to it any other way. Because multiplication is just really a fiction. I make it up. I take 3 times 3, but how do I get the 3? In order to get the 3, I got to divide something to get to the 3. I divide the whole in order to get the 3. And suddenly I'm into a big conversation about fractals, and then my mind blows up. Oh, it's just a wonderful feeling. So we're going to be able to talk about some of that tonight in a major way. Richard, I'm still looking for that Jane video where Jane 108 sat and explained. He took a tetrahedron and then took an octahedron, cut it in half, and then took the octants in the upper half of the octahedron, stacked them together with the tetrahedron, came up with a cube, and called it cube thinking. You sent out the coolest video on that, and I've looked all over for it. Do you have? Can you find that thing? Do you think?
Yeah, I'll give it. I thought I've had it here. Anyway,
So,
yes.
yeah, try to, don't try. Please locate that. I learned what an octant was. An octant is 1/4 of 1/2 of an octahedron. So if you take an octahedron and you take it in half at the base, so now you have 2 pyramids, 2 4-sided pyramids. And then you take each one of those, or you take any one of those pyramids and cut them into 4, those are octants. And so the 4 octants added to one tetrahedron produce 1 cube. And Jane did a great graphic. I have checked Jane's website. I've checked my emails. I was sure I'd saved it. Are you having any luck or shall we just start reading?
Yeah, start going and I'll,
Okay. So we're on page 171, and I'm going to make this bigger so it's not quite so difficult to read. And then we'll go from there. Let me see, 171. Where's page one? Okay, it's down at the bottom. Okay, good. Oops. All right, so here's where we start. Vector equal, oops. What's my page number? 173. That's very interesting. So
It's
what's that?
correct.
Yeah, so I'm
At 10 after figure 10.7.
yeah, and I'm at 10.7. I was bigger 10.8. There's 10.7. There we go. Vector equilibrium. Vector equilibrium. I'll read a page before my mouth falls off. The volume of the VE can be quickly determined through direct observation. Recall the 12 unit length radii outline 8 regular tetrahedra and 6 1/2 octahedra. This fact, combined with our newly generated volume data, provides a conclusive value for the vector equilibrium, 6 1/2 octahedra, each with a tetrahedron volume of 2 plus 8 unit tetrahedra yields a total tetrahedra volume of 20. 12 plus 8 equals 20. This simple breakdown supplies further evidence of a natural order of precise volume relationships and is especially reassuring that a unit length vector equilibrium, the conceptual foundation of Fuller's energetic mathematics, falls into place with its own whole number volume ratio. Cool. Any comments or questions on that? I'll tell you, I read the words and they kind of floated by.
Can you
Rhombic,
go,
what's that?
can you go back a
Yeah, I'd
little
be
bit?
glad to because there we go.
Yeah, anyway, it's just, oh, sorry, down a little.
Oh, that's okay. Here are the 4 octants of the octahedron. And you put or here's one of them, 2, 3, and 4. You wrap them around a tetrahedron and you come up with a cube.
Nice.
And then this gives you this gives you a formula. I'm not sure I understand 6 1/2 octahedra, to tell you the truth. So anyway,
It's just interesting. I mean, the last line just really kind of struck me as well. The simple breakdown supplies further evidence of precise volume relationships, and just how that relates to simplicity,
Yeah.
and how we actually kind of reduce things, and that kind of gets to this whole idea of understanding the patterns of division and multiplication by division. What it really means, it's an element of simplicity that comes with that. Anyway, that's something I've been thinking about quite a bit. And that's been, exciting. But it also gets into the efficient use of space, which is something obviously we've talked about extensively here, even going back to the cookies on the tray, the 13 versus 12. I believe. So anyway, yeah, go.
No, go ahead.
I'm done.
Well, I'm trying to I'm going to look back and find that table where it shows the volumes. There it is right there. This is back on page 91 in the book, where it shows the volumes as they read in whole numbers, as they relate in whole numbers. And that's what we were just referring to. That's the part that we just read right there. And I'm having trouble connecting it all, but that's where it's at. So we can continue with rhombic dodecahedron if everybody's ready to go. Richard, have you been able to find that link?
no, I'm still looking.
Okay, wonderful.
I had them, I saw them just earlier today, I think, but no, I don't know where they are.
Wow. Rhombic dodecahedron. To begin with, our recently disassembled octahedron must be put back together octants are thus lifted away from the composite cube, figure shown in 10.6, and their right-angled corners are again turned inward to meet at the octahedron center. Next, we divide two tetrahedra into quarters. Each tetrahedron yields 4 shallow pyramids, encompassing the region from an outside face to the center of gravity in figure 10.8. We can hear you. Okay, thanks, Richard. As before, the equilateral base of each shallow pyramid allows for the 1/4 tetrahedra to fit directly onto an octahedral face, and as soon as 8 1/4 tetra are attached to the octahedron, a rhombic dodecahedron emerges. See figure 9.12. And I'm pretty sure this is 10.8. Geez, see figure 9.12, that's in the previous chapter. Let me see what page that's on. Let's see figure 9.12. 9.12 is on
Two
page
units of
150.
volume have been added to the octahedral floor. Okay.
And it's inviting us to look at unit figure 9.12, and that's on page 155. And if I add 28 to it, that makes it be 183. So if I come over here to 183, I should be able to find it.
Huh.
183.
Oh, wow.
That's figure 9.12. Is that the figure to invite us to look at? I think it did.
Yeah.
And so there's your octahedron, and this is creating the stellation of an octahedron creates a dodecahedron, evidently. Very interesting.
Huh.
Somehow this has to do with multiplying, dividing
Oh,
and
yeah.
multiplying.
Everything else.
Yeah. All right, great. Rhombic dodecahedron.
Yeah, you
And we
finished
just
that.
read that. Yeah, we
two-
finished
yeah,
that
two, yeah.
paragraph. Okay, good. 10.8, subdivision of a tetrahedron into 4 shallow pyramids. Whew, beyond me. Anybody else want to read?
Sure. I mean, I could definitely do it.
Okay, hang on. There we go.
Subdivision of a tetrahedron into 4 shallow pyramids. Looking at the shape of the rhombic dodecahedron with its strange angles and facets, the perfection of this whole number volume relationship seems particularly remarkable because both shape and topological characteristics of the
Oops. Hang on a second. Sorry.
tetrahedron.
So sorry.
No worries.
Okay, 172.
Characteristics of the tetrahedron and rhombic dodecahedron, or hang on, I can't really see.
I know. Here we go. There we go.
All right. So yeah. All right. Rhombic dodecahedron appear utterly dissimilar. The discovery of this orderly relationship between the two polyhedra adds significantly to our growing sense of an underlying spatial order. Again, the considerable flexibility of the IVM framework enables us to plot all of the above polyhedra with the IVM and IVM vertices. The rational rationale for using the unit diagonal cube also applies to the rhombic dodecahedron, which arises naturally out of the interaction of IVM and IVM cells. Recall that every octahedron in the matrix is surrounded by a quarter tetrahedra, thereby defining rhombic dodecahedra with unit length diagonals. We discovered many shared symmetries in the previous chapter by dissecting the IVM, and we now developed a significance of these observations with the discovery of the rational rational volume relationships inherent in this framework. Bucky was not the first to discover these ratios, but he may have been their most visible spokesman. He brought the esoteric information of the attention of countless packed lecture halls as one of the more satisfying indications of the fallibility of our coordinate system. Such sublime disclosures by nature must not go unheralded.
Let's just take a second and acknowledge that
Yeah, let's
Manu,
definitely,
Manu
yeah.
joined us.
What?
Manu,
Oh, hey,
Manu-
Manu. Hey,
yeah,
what's up?
Manu joined us. So cool. So does anybody want to welcome, Manu? How are you feeling and what are you anticipating for today?
Feeling good.
Good.
Feeling good for women because it was Women Day yesterday in South Africa. In South Africa, in 1956, I think, 20,000 women decide to march on the Union buildings in Pretoria in protest of apartheid. And they burned the passbook because Black people needed passes to go from one place to another. They burned them. And this is today, you know, a national day in South Africa is a National Women Day. And August is a Women Month.
What happened to them for doing that?
They were arrested. They were beaten. Some, you know, in those days. That is almost 70 years ago. Otherwise, I'm very happy. I'm humbled to be among you guys, and I see that you have been progressing a lot without me. I have to play some catch up and get on the train and be able to participate meaningfully. So that's the way I feel. That's what I expect to do. Back to you.
Cool. Let's continue reading. Did anybody have any comments on what we read? Thank you for sharing, Manu.
Maybe.
What page are you?
We're on page 172.
Okay. All right.
I guess we're on page 173. This is page 173.
Yeah. I just heard one word and I've been thinking about it. Rational numbers has to do with symmetries. Has to do with proportion of symmetries. If you take the definition of rational numbers from Wikipedia, from the thing, rational number is the number that can be expressed as the quotient of a fraction of two integers. Integers are whole numbers, like 1, 2, 3, 4, 5, 6, 7. And integers are made of two, of the odd number and even numbers put together, plus 0. That is the set of integers. And in the thing, it say the rational number is a ratio of any of those two. But that stops there. It doesn't go further to say for why is it irrational? Because we if we do 1/3, 1/3 is infinite. Is a series of, you know, is what 1/3 is 0.333333 ad infinitum. It is a rational number. But from experience, because we calculate it, it doesn't yield thing, we call it irrational. It's not. It is a rational number.
Right.
It's a ration of one entity to another entity. One finite quantum of energy to another quantum of energy. And it has to do with the ratio of the vectors of the IVM to the structures that we build. And remember, you do that based on symmetries, based on patterns. Symmetry may also be associated with patterns. Because the pattern in whatever that we see, it is a set of ratios that have been together, birds of the same feather is the pattern. And they flock together. Birds of the same feather flock together.
That's interesting the way you just put that, made it really, really clear. The relationship between two entities, and if we looked at the numbers from that perspective, just, everything makes sense. And that's how you kind of come up with the whole system.
You remember the IVM is one everywhere. One everywhere.
Yeah.
It's wherever you look, it's like you are at the center of a sphere and you are looking at every direction. You have a radius that goes out with amplitude 1. It's the same stuff. Wherever you look at it, you see the same pattern. That is the IVM.
It really is key to understand the IVM.
Yes. The IVM then is the original steady vector. Not vector, the original steady system of energy. Let's just put it that way. The original steady system of energy. If there were never any disturbance, the IBM would be like dormant because every flow loops in the same way. It loops in the same way. If now there is disturbance, you should assimilate it to our dividing, where a cell inside the IVM sleeping. So it's a strike on the IVM. Because we wake up, we start being aware. And when we start being aware, we say, hey, our mind say we are aware of the otherness, of something else. So we start dividing. Where we strike, we have a ratio. And then we have a length, let's say an amplitude of our strike, where we throw our line. That is a radius. And that radius now, we have to make sense of it. We have to compare it to something that is natural to us, that is natural to our fabric, that is natural to the IVM. So we compare it to the cube octahedron of the IVM. Because we know that the IVM is made of the tetrahedron and the octahedron that are concatenated all over. For a cube octahedron, we've seen that very clear, right?
Mm-hmm.
Universe can be simplified into two things that are one into the other like this, that are put together like that. That is the octahedron and the tetrahedron and 4 tetrahedron. That's universe. And the whole can also be folded more into one original tetrahedron. We've seen that. Now, when we start dividing, that is unfolding. That thing. Dividing, unfolding. Then, discretely, there are ratios.
Mm-hmm.
Thus, the rational numbers. The rational numbers don't describe the whole set of numbers.
Right.
It is a subset of numbers. One, the very first subset, that is the most dense, is the integers. The positive integers, that's the one that we see, and the one that we don't see, that is their negative. We say +1 and we say -1. -1 is getting to us, +1 is getting out of us. Those are the integers. Then the next thing that we see is are there ratios? Are there things that if you divide together, year, the same result. Like 1/2, 2/3. 1/2, 2/4. 4/8 of 1/10, 2/6. Sure. And that is the rational numbers. So those rational numbers yet don't describe the whole set, because there are still things that are irrational. Right?
Yeah. I mean,
Yeah.
it actually is.
Yes. What is irrational is something like the phi. Phi is still within our system, but it's irrational. You always get into it to phi. You will just approach it, but will not get to it. And those are everything that got to do outwardly towards the shell of our sphere, or inwardly towards the shell of our inner core. The macro and the micro. But remember that that approach of it is still within the concave space, right? Within the concave space. Now, there are other numbers that not only are irrational, that is not the remainder of what it is in our structure, but in order to invoke our universe, we have to like invoke them. In order to talk about universe, we have to conjure them. It's no more within the realm of our rational thought. It is like, it is part of a fabric from outside of us. And those are what we call transcendental numbers. One of the most known of a transcendental number is pi. Pi is intrinsically related to the notion of sphere. Pi is transcendental to the structure that we can divide. Remember that we obtain structures by dividing the IBM. And pi, you cannot divide the IBM and find pi. There's no way. We have to invoke it from outside or from the fabric of our shell, of our sphere, to say we have a sphere. Because we imagine that we have a radius. And then we know that we have a radius, and then what is the contour of that radius? How do we measure it? We have to invoke a number that is not within our set to say that if we multiply that radius by the circumference, if we multiply that number by the radius, we get the circumference, or by the diameter. And we always invoke that because to talk about the diameter is through symmetries, right? The first, I'm in a cave. I imagine that everything around my cave is the same. So I can get out and measure my cave as a sphere or as a circle. And I imagine that every layer that forms me goes out, infinitum as a circle. And every time that I do the ratio of this divide by this, that is the diameter, I find the same number, 3.14, etc., etc. But there's nothing that I can do to say that it's 3 for 14. It's like given to me from outside my system. That's why it is transcendental. The second transcendental number that we know is the base of our counting, or what we divided. We know that we count by shells, by layers. 1 layer, 2 layer, 3 layers. That's what we count spherically. That's what Steve always says. We don't count linearly, we count spherically.
Right.
And to count spherically, the ratios became exponential, logarithmic. We cannot use a decimal accounting for the logarithmic accounting that is required because it's expand like this. And the surface of it,
Mr. J.
Yes, expand like a square. It doesn't expand like double. It's a square, 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 square.
Wait a minute. Can you go back over that last part? Why we can't use decimals?
I'm saying when we count,
Oh,
we are counting
Okay.
units of energies.
okay.
And that unit of energies, or the first principle is that energy is all around us.
I misunderstood. Sorry.
Yes. So we are counting a layer of energy around us. To count that layer of energy, you cannot add the first layer to the second layer. Just add like this. It wouldn't yield anything. It is a square. It is a surface. The thickness can be the same, the one that we see, but that area there increased like a sphere, like the square over radius, right? Is again pi multiplied by radius square. Steve always draw that. You remember the segment that he draw like this, coming out? And Steve, how do you call that area?
No, I don't know.
Yeah, you always draw that. You draw from a center, radius like this, and you see the layers. The layers increase as squares. Anyway, as squares of radius. So if they do that, you cannot add them. You have to have a new base for that. A base is a unit of measurement. And then thus, we invented what we call the logarithmic scale. And we say we have a natural logarithm. You need to have a base. And that base is what we call the Neperian number. Neperian. Neper was one of the first mathematicians to make that popular. We call it the Neperian. He was an Englishman. So Neperian is the Neperian number, the base of it is E. When you say exponential x, for example, that E is a number that is 2.71 something, infinitum also. Is also another rational number. Irrational number. You know, another transcendental number. So you see that in our accounting of universe, we went from the whole. My cave is everything that I know, the IVA, to the ratios, to the remainder of after the ratios. What is remainder of after the ratios? We call them irrational. And then
Wait a minute. When you say remainder, is that kind of what's left over? Same idea?
yes,
Okay,
that's the phi.
yeah. Right.
That is the phi. We also saw phi. We defined phi as a remainder. You remember that?
Yeah.
The dampener of our structure. We say the phi was that thing that we mute like this to allow the resonance of a music play, to allow the song of nature play. Our fingers come and dampen at certain point. I'm not a musician, but I'm holding like Steve would do. It dampens those and allow then the different wave, very constrained, to play, and that is a structure. We should then always see what we call structure as the build that we have in nature, like this house. No, it's more than that. Every time that Steve put a note that makes sense, it's build a structure. Because out of it comes an acoustic energy that stimulates us in a certain way. Steve has taken energy and directed it in a way to achieve a result. The result is to please us. That's why they call them entertainers. They're entertainers because their role is to take us from one state, maybe of sadness, to a state of exhilaration for a time. So the time of play of Steve, of a song, he's built a structure that is expressing what it was built for, music. You have to relate all of these things. But
Okay.
that music, everything is muted around it and it's playing. It doesn't mean that is the whole stuff. There are still things that are remaining within it, the structure, that are not rational, that are not in the pattern that Steve wants to play. We build structure, or structure exists for a purpose. That's why structures are polarized. They have a direction. They're going somewhere. Anyway, my point was, those numbers are very well in mathematics. You study mathematics well, you see that they study them, but they never tell you where they come from. They just say, okay, let's study irrational numbers. Or they say they are transcendental number. I don't know if you remember your first lesson where they introduced the logarithm and the thing to you. It's like when they introduce time. They never tell you why there's time.
So true.
In primary school here, they call that complex numbers. Why is it complex?
Right.
To introduce time. They are
That's
unable
the
to
word.
tell you that time is a consequence of a natural phenomenon that's lag. Because we see things with a lag, it has to repeat for us to see. And the repeat is a natural stuff because everything orbits. Orbiting is a natural, it's part of our fabric.
Okay.
Orbiting. I'm through there. Sorry
Is there
to
any-
interrupt
any-
you, but
any-
I wanted you guys to divert you. You were too serious when I came into this stuff.
Any questions about what Manu has been talking about, or shall we continue with the reading?
No, I mean, it's actually just really been, helpful. I mean, just walking through that process and understanding the difference, with what.
Okay. Do you want to continue reading?
Yeah, sure. Yeah, I can. Especially the what's left over part is actually really interesting. So
If you want to comment on that, go ahead.
no, I mean, I'm just thinking about that in terms of how there's an infinite number of possibilities in the universe. So
Okay.
that's all. And I'm just thinking about that and how that actually works and with like something like a fractal.
Cool.
I'm still trying to figure that out. I'm trying to articulate it. I'm not the best at that. All right.
You can either articulate or read, whichever you care to do.
I mean, for the betterment of all of you, I'll read.
What page? What page is exactly there where you are? What page?
173, I think.
I have my book.
We're on
That's
page
173.
173.
Okay. Right. Thank you. Sorry to interrupt. That's fine.
These volume ratios is provided by Fuller with a powerful source of confidence in the legitimacy of pursuing synergetics, and indeed their significance is worth our serious consideration. What accounts for the lack of attention paid to these simple mathematical facts? Job offers the following explanation. When these relations are derived with the aid of the usual formula, for the volume of a pyramid, V equals 1/3 AH. Am I saying that properly?
I think so.
Okay. A good many irrational numbers are involved, and the simple integral ratios emerged almost incidentally. Somehow these simple integral values of the volume ratios of common solids are not part of our scientific culture, and a lack of familiarity with them frequently leads to unnecessarily cumbersome computation. It appears that a bias of our culture to orthogonal Cartesian coordinates, we've talked about this quite a bit, has obscured these relations. Multiplication by division. Bisecting the edges as before, we take special note of the tetrahedron square cross section. This fourfold symmetry was a significant factor in the previous discussions, notably in the sphere packing demonstration, in which two sets of spheres came together at 90 degrees and unexpectedly, I'm assuming, produced a tetrahedron. However, this aspect of the tetrahedron is easily overlooked as a triangular pyramid with its preponderance of 60-degree angles. This shape is easily perceived as a completely triangular affair. Suppose we ask the following question: how much of our cheese tetrahedron would be chopped off when the newly exposed surface created by the slice is a perfect square? Without a certain amount of previous exposure to the tetrahedron, your reaction would probably be the slicing plane could never be square. It might be a very small triangle or any number of larger triangles as you position the knife closer to the base. But a square? Wait, the tetrahedron has four faces. Do they somehow outline a square? Anyone who has read this far knows the answer. But countless students challenged to find that hidden square have been struck. Handicapped by the perpendicular bias of mathematics, they are unable to find the square cross section in the exact center of the tetrahedron, which, once seen, is unmistakable. Stuck, not struck, by the way.
Yeah. You know, I always enjoyed the way Kelly, when he showed a picture of a tetrahedron, it wasn't sitting on its side like this. It was sitting on one edge or the other. So like, and I think if the tetrahedron is sitting on its edge, it's much easier to see that square.
Yeah, it is.
Um,
It's a lot easier to see that square.
Yeah.
Yeah, but the problem is that in the mind, they always cut the cheese perpendicularly to the surface of the table. In order to see the square, you need to cut at an angle like that. I have my cheese there. I have my cheese here. And I have to come like this in order to see the triangle, the square. If I cut it like that, in that plane, it's going to show me the square.
Can you take the book down?
Yeah.
So,
Yeah.
If you look at this
If I
puppy
cut
right
it,
here,
if I cut it like this, I'm going to see, because I'm going to see this line and I'm going to see it here also. That is the square.
so by
You see
holding the tetrahedron on its edge instead of on a face, by holding it on an edge, it's very easy to see that when you stick a piece of, when you cut it right through here, bammo, you're hitting all four edges.
Yes.
You cut through there.
Yes.
That's easy
And
to see.
it is because they have been trained in the mind to have this table, this desk like this, that is flat horizontal, and the knife come like this.
Right.
So everything is resting on the table. If you take that now, if I take my tetrahedron and I say, okay, this is my surface table like this, and I'm cutting, I'm never going to see it.
Right.
I'm reducing one dimension by cutting like that orthogonally. I'm just going to see a triangle.
You're right. That's why holding it on its edge was kind of unique. And Kelly used to show the tetrahedron sitting like this.
Does anybody know how Kelly's doing? Just, I'm sorry to really
No.
go off on, okay. Just,
I think our last report was from Wayne and he was doing fine, but just barely doing fine. So anyway, so there's the 4. Any other comments or questions on that?
no, but I appreciate that example.
Okay. So you see, if this thing weren't laying on its face, if this thing were laying on its edge, instead of on a face, that would be an easy piece to see.
Mm-hmm.
And I think it's pretty easy when you look at it like that.
But
And you can-
again, look at the link to one thing natural. We don't know that we are zooming and spinning in the universe, being on Earth. So we imagine that our table is always horizontal in front of us. We go to sleep, we wake up, we see a table, we say, the angle was the same in relationship to the reference of universe. No, it has moved. So there is infinitely more times when our table will be at angle than at it being horizontal, than at it being like perpendicular to a vertex.
Yeah, my bed influences my paradigm.
Yeah.
If I slept standing up, it'd be a different deal, but I sleep laying down. Isn't that interesting? Okay, good. So there's that. Figure 10.9, 2V tetrahedron with 1 octahedron core. That is that implied octahedron inside there. And of course, the base of that octahedron is exactly the square we're talking about over here.
But Steve, people realize not how powerful that B, that figure 10.9B is. It is foundational to everything. 1, we know that universe is finite.
Right.
And we know that universe moves. It's deformable. If it is finite and it's deformable, we know that it can be folded and folded and folded until it can no more fold. That is the tetrahedron. We saw it the other day that if you take a sheet of paper like this, that appears flat, you could fold it, you could fold it, you could fold it. We saw this thing. We did this exercise.
Until you get to its most simplest
Yeah, you
form.
could fold it. This is folding.
That's
You
interesting.
fold it, fold it, fold it, fold it, and there I have the tetrahedron. It was one sheet of paper. There it is. It is folded into a tetrahedron. Right. And you can unfold it. So the first thing is we can fold to a minimum.
Mm.
Richard,
and remember, we are unfolding rationally. You know, we are unfolding, there's a rotation and spinning that we do, and then we hit a number that is stable. And we've never talked explicitly about the degree of stability here. The tetrahedron is the most stable, the most compacted. The octahedron is stable, but it's less stable than the tetrahedron. You know that? By order of degrees. The octahedron is less stable than the tetrahedron. When you talk about any system, the nucleus of a system is tetrahedron.
The tetrahedron, yeah.
Mm-hmm.
Yes. And when you expand it, and it's like natural, when you put more energy, it becomes less stable. Now, when it hits a fractal, the octahedron is a fractal.
Yeah. You can
Right?
absolutely see that.
And then the other day, yesterday, I was running, and then I was saying, there's a way of representing it. That you take, you know, the way we show stability now by showing a receptacle that is an hemisphere, that is convex. If you take a pot, you know, the tripod, the old tripod of your mom, right? You remember the old tripod for cooking? You guys are too developed. If you live in Africa, we used to have aluminum smelted in the form of a copper, in the form of half a sphere, an hemisphere like this. And then you cut it, it's like that, and then you have tripod. You have 3 legs. And you put it on the floor, and then you light, you know, like a fire under it. And then that's where you have your sauce, you know, for the whole village. You know, you steer your, Richard must know that thing. You know, he's been to India and to Africa. He must know it very well. And Steve also must know from being with Indians.
Indians
Remember
didn't
the
have
big pot?
spheres.
Yes, but my thing was this. I drew this yesterday. It was a note. You see here.
Hang on a
Take
second.
this, and I'll show you.
Okay, move it around a little bit so I can see it. A little closer. Closer. Yeah, okay, good. Now tilt the front of it. Yeah, tilt the top of it. Yeah, okay, good. And there we go. I got it.
Okay, can you show it, and then I will be able to explain more.
Here we go. Okay. I'm going to make it small just for a second. And then I'm going to make it big again.
Steve, I must come to Tulsa, and then we work together, really, because I don't know how I'm going to carry these papers.
I'm aware.
We need to put them. Yeah, I have tons of papers, not over the years. Okay. Can you see that?
Mm-hmm.
I was just running, and I first defined me as a tetrahedron. Eh? It was just, I say, just show the top first, you see? It's a diversion, but you make us lighten out. I was running, and I say, hey, I'm a system, I'm complex, I'm dynamic, I'm adaptive. That was my tetra word yesterday. Okay, let's go down now. And you see tetrahedron there, right? In terms of volume, yes, it is small. It is the smallest. It is a volume 1. But if you want to represent it in terms of stability, like the pendulum, you know the experience of a pendulum, where you put a sphere rolling into an hemisphere. How far can it go before it hits the boundary? It's the maximum. You see that? That angle? It does this. It can go up and down, up and down, up and down, and coming back to the same position at the bottom.
Right.
Like this. Friction will make it come back and sit at the bottom in the trough.
Right.
Everybody has done that experiment, right? You take a ball, and then you put something inside it to play the pendulum, and you roll up and down and come. That's the way people define stability, right? But now, if you take the octahedron is a volume 8. The octa is a volume 8, and you see it is, in order to define its stability, you need less volume. Your pot to define it in terms of stability will be the lesser pot. If you push it too much, that is, if you amplify it too much, it's going to go out of a ball. So it's a fractal of it. It's stable, we feel a more constrained space. And you go to the icosahedron. The icosahedron is 20 volume. The icosahedron is 20 volume of tetrahedra expansion. So you see its own domain of stability is much more restrained. Now let's take a cube. The cube is of volume 6 tetrahedra. But if you want to represent its stability, it is actually the cube is at the top of a concave thing. You push it a little bit, it goes away, it doesn't come back. You see that?
Mm-hmm.
The cube is not stable. It's interesting to see that the regular rhombic dodecahedron, which is of the same volume as the icosahedron, because it's a dual of icosahedron, is a star, is exploding. It's exploding like the cube. The cube explodes. The cube is not a black hole, it's exploding. The dodecahedron also of 20, it goes that way. It is when you take anything, let's just take the representation of this. This is the stable part into this, but what goes into this hole is the star dual of it. This energy is going out here. Energy is trapped in this, energy is going out through the windows. And the two together always make a stable system, a dual system. I don't have one here. This is the icosahedron. This icosahedron here is it. If you expand it, normally in the expanded form, it is as if you put it in with its dual. You will have the icosahedron cut this way. Do you see this?
Yeah, actually.
This is the same. But you see here, if you take the icosahedron cut that way, that is it. Because the icosahedron has 20. You count this. There are 20. This is number 20. Do you see number 20 here?
Yes.
Okay. These are 20 equilateral triangles at the surface. And each of those triangles is only joining at vertex to vertex. That's why it's the most explainable. That's why it's the gaseous form of our universe. It is stable, but it's gas. Right? You see that? It's only vertex to vertex. But do you see this hole here? Look at the surface here. What is it?
A pentagon.
Exact.
Mm.
That is a rhombic dodecahedron. Huh? This is a rhombic dodecahedron. You have two pentagons at the top and at the bottom at the poles, South Pole and North Pole. And you have zigzag. Zigzag here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 around the equator. That makes the 12 vertices, like that of the icosahedron, to defining universe. When you concatenate these two like that, that is, you put them together at 90 degrees, everything is compact. You have that's again the duality at play, right?
Mm-hmm.
Sorry for my right, but I like to land there.
That's fine.
But that's
Right.
it.
Here's another part to that.
Yes, Richard?
If you've got 12 12 vertexes, and you add one more, you've got
12 faces.
you've got 13 things, gumballs, and the instruction is put them together in such a way that you create 20 livable spaces.
Yes, I have 24. Remember that if I put this.
No, 20.
Hold on.
Oh,
I have 20. Yes, I have 24. But I have the poles and the equator. That are direction, which I take out. Those 4. 20 are left for the exchange.
But what I'm doing in terms of an exercise is saying you've got 12 things. Well, you got 13 things, and now put them together with as many edges as you want, toothpicks, and create space, volume space for 20.
Yes, exactly. And that's why they say the icosahedron is the most expanded stable form of universe. But when they say that, they don't explain to you.
But how do I put 13 things together in such a way to create 20 spaces, 20 volume spaces?
This is 12 things that I can count because I can count the vertices, yeah? This is the icosahedron I can see. And this guy that is not visible, the other guy, inside, in a way of the dual tetrahedron, vertically, to fill these forms. And when we talk, usually, when we talk about the relationship, we never talk about the role of that, the dual tree.
But you're not following my instructions and telling me how you're going to build 20 spaces with 13 things.
And you're talking about
Duality.
13 vertices, right?
Well,
No, there's not 13 vertices.
No, you've got 13 things sort of like vertices, yeah, but think of it you've got 13 gumdrops, and you've got as many toothpicks as you need, and create a space that would accommodate kind of a volume of space for 20
faces?
20 houses. No, not faces, 20 spaces.
Do you have a picture of what that looks like when you're done?
Well,
okay, let me tell you what I'll do.
Okay, you do it.
Answer your question. Okay. Let's just say I have 13 tetrahedra. 13.
No, 13 things.
Yes, I call them, yes. A thing, anything can be compressed into a tetrahedron. I'll take 12, I'll first make this. That's the complete word. And the other one will be standing aside like a tetrahedron on its own. And I'll play the dual role between these two.
Yeah, but how do you make 20? How do you make 20 spaces?
Okay, here
I'll put them. Hold on. Okay. So I have this icosahedron that is 12 tetrahedra. We have that here. I build this. I take the other one, I divide it in such a way that it is an icosahedron and a rhombic dodecahedron. I take that and those things in the rhombic, the isocahedron, and the rhombic dodecahedron in a dual relationship. I have 20. And I have 20 because when I put those together, unity is plural at a minimum of 4. I have the 24 elements minus the 2 poles here, minus the equator there. It gives me 20 relationships, 20 units when it put together. Okay, so that was my tentative answer, Richard.
So Richard, how would you do it, or what do you say the answer is?
Well, the way you do it is you take the 12 we were talking about, the vertices, and then you take the 13th one and you put it in the middle, and then the 20 triangular faces of the icosahedron is you then take those three of each triangle and then angle them down with your toothpicks to the center one, and you will create 20 tetrahedral spaces. And this is kind of an exercise of how you take 13 things and turn it into 20 livable spaces, let's say 20 sort of units, that bachelor units.
Richard,
that way.
you compress one thing. What do you call put in the center? How do you
Pardon?
put in the center? You say put in the center, you take one thing, the 13 thing, you put in the center. How do
Yeah.
you put it? How do you put it?
By just putting it in there.
Yeah, with
And-
No,
toothpicks.
you don't just put it in there. There's a construct.
Okay,
Right.
fine.
Yeah, because when I listen to you, you say exactly the same thing I say. When I take one tetrahedron and the other tetrahedron, one tetrahedron that is concave, this one, isocosahedron, is a concave tetrahedron because it can be compressed, all of this. I take another tetrahedron that is convex, but both have poles, and I put them in orthogonal relationship like this, one perpendicular to the other. I have what you say.
Yeah, I know,
Because I
but
have
and that's important to know, and very, very helpful, because it's you using your way of doing it, and I was offering my way by way of a sort of a question to try and see if you could do it the way I was setting it up.
I 100% agree with you.
But
I 100%
anyway, that's
Yeah.
that was just a little lesson that I learned from Bucky somewhere along the line, and it was always a fun exercise to give people 13 balls and as many toothpicks as they wanted, and create a space for 20 livable bachelor unit, if you want, spaces.
And what is that,
and-
Richard? What is it that you've done? Multiplication by division. You've just done the magic. You've multiplied by division. And that's what most people don't get the mind wrap around it. They don't understand it. It is an orthogonal relationship.
Okay. So you have one gumball in the middle, the other 12 are around the outside like in a sphere, and you've just used enough sticks to connect them all into one unit with one gumball in the middle and the rest
Yes.
around the outside? Is that
No,
what you-
what
Yeah,
he forgot to
what-
tell you, Steve, is that the
Richard.
gumball in the middle is radiative.
Yeah,
you-
so
you-
that's
you
what you're
have-
doing, right, Richard?
If you have your basic icosahedron just the way he described it, and you've got the 20 20 triangles, 20 faces. So you've got 20 triangles that have three edges that make up the triangle. Then what you do with the one that's in the middle is then you take your toothpicks and you connect your three vertices on each triangle back into the center one, and
Right.
you've created a little tetrahedron. And you end up doing that with all the faces, and you have 20 livable space tetrahedrons if you want.
Really cool.
And so the idea behind it is that it appears impossible, if you want, in the beginning, for someone to sort of say, well, wait a minute, I've only got 13 things. How on earth can I create 20 spaces? That's the challenge, to get your head around doing more with less. And I have a model here where I set this up as a part of an exhibit at the university when you had all the faculties come together and display their their goods, and you have new students coming in, and everybody's trying to say, well, come and study in my program or come and study in the other program. Well, the engineers and people like engineers could always attract the biggest crowd because they had models and workable sort of machines maybe. And those of us in the soft sciences had nothing other than our own sort of expressive language about what we're all about. So anyway, I set this up and I invited people to come and talk at our table, but then I would give them this, and I gave them 13 gumballs and a whole bunch of toothpicks and asked them to construct what I was just talking about. And if they could do it, they'd get a prize. So lots of young people came and they walked away with this thing. But the young son of one of our support staff, he came along, he took that package, he took it home, and his mother told me afterwards, and he assembled that structure within 2 minutes. And I saw her not so long ago, and the son now is 28, 29, 30. He's an engineer in Asia somewhere, having a great sort of occupation and profession. But he had that creative talent to see how you could put all those together, and he came up with this structure. Anyway, it's just another way of trying to use examples to help get points across in the kind of way I was doing it, and then with the way Manu does it, then we get different ways of being able to see maybe the same thing.
Cool.
Okay. Can I share something, Steve? Just 2 minutes.
Okay. All right.
Okay.
2 minutes.
Yes.
I'd
see
like to
this?
read some more of this book. Go ahead.
Okay, I've just taken 2 minutes. I'll give them back in my share.
Okay.
You see this? This is the real icosahedron. Because the icosahedron that we see compact like this icosahedron doesn't exist. It does not exist. It's a form. We imagine the real icosahedron is always with its door, right? Now, imagine that I have this now. If I do like Richard, I put, so this is like this triangle is here, the 20. I put a lantern in the middle of this. What will happen? In the lantern is a source of light, is a star. Light will come through these pentagons, right? All over.
Right.
So I'm not going to see anything of the pentagonal, right? I'm just going to see a star. But what I see is what is reflected in the form. I will see the 20 faces of the icosahedron if I'm looking from outside. Do you understand the experiment?
I think so.
Okay, that's all. If it took 2 minutes, that's fine. If it took less than 2 minutes, I'm okay too. All right.
Cool. Any comments or questions?
This is the kit that the 8-year-old put together over 20 years ago. I still have it. The gumballs are a little hard, but
Yeah, that's exactly it. Yes. What you will see is the reflection on the icosahedron, because light, pure light, is the IVM. You don't see anything.
So show that again, Richard, and back it up so we can see the whole thing, please. And I'm going to see if I can. Holy macro.
Can you hold it slightly higher, Richard?
Wouldn't try and chew those
Oh, yeah.
pieces of gum.
Wow, that's really weird. Oh, there we go. Okay, good.
It's not weird, Steve. You always think that
Is that
nothing
gum?
always show itself alone. You always show yourself with your doer. It's a permanent relationship. You have to train your mind to take that.
Show that thing again one more time. Richard, and Joe asked a question.
No, I was just, I was wondering if that was actually gum.
They're gumballs, right?
Yeah.
What do you call those?
I don't know.
Well, they're just sugar gumballs.
Yeah,
Yeah,
really cool.
I think the main point there is that that structure that is seen around will not exist without its core, without the referential where you have the vertex spring. It will never exist. The two are always is one whole. You see the 20 faces because that one exists, because it was the radiative part that was in the middle that we don't see and we ignore it. We think that it doesn't exist. That's why we
Cool.
have so much difficulty. Okay.
We
Yeah,
have a couple more.
What
Go
this
ahead.
young fellow did, which is always interesting, the way it was set up, and all you have is these gumballs and toothpicks. And when he put it together, what he built was an icosahedron. And wasn't that we were trying to give him the instruction of how to build an icosahedron, the way he put it together, and it worked. In a natural process way, he built an icosahedron. And it happened to be one that has a kind of a volume element to the spaces, so that he created then 20 tetrahedral sort of spaces in with that octahedron outside sort of 20 triangles, the 5 in each of the pentagons, the top 5, the bottom 5, and the 10 all the way around gives you your 20.
Cool. Okay, let's see if we can finish reading these last couple of pages to finish off this section.
Mm-hmm.
Joe, do you remember where you were?
Yeah, if you put it up.
Were you here?
I can't see it. Oh, yeah.
You was
no,
at
Yep.
10.9b.
Yep.
That's where I interrupted, yes. Sorry.
No worries. The square in figure 10.9 is parallel to and between two opposing edges, which themselves are perpendicular to each other, delineating the square cross sections corresponding to each of the 3 sets of opposite edges. This aspect of the tetrahedron symmetry is exhausted, and the 2-frequency subdivision is complete. A total of 12 new edges outline the octahedron, and by now this relationship is quite familiar. Figure 10.9b.
That's the octahedron inside of the tetrahedron.
Mm-hmm.
Okay, cool.
We continue inward, this time bisect.
Sorry.
No, that's all right. And interconnect the edges of the octahedron. The process is equivalent to Loeb's degenerate truncation. Or was it? Yeah, and then okay, and outlines the edges of a vector equilibrium hiding inside the rectangular octahedron. Figure 10.10b. We could continue by joining the midpoints of the vector equilibrium edges to produce a rhombic octahedron.
Rhombic cube
Cube
octahedron.
octahedron. Sorry, yeah. Anyway, yeah.
It's okay.
Yeah, it's I should yeah.
Or
Anyway.
rhombic dodecahedron.
He calls it a cube octahedron.
Yeah,
here.
yeah.
She
what I-
calls it.
I
Yeah,
was
go
looking
ahead.
for yeah, actually that's interesting. However, Fuller's sequence comes to an end at the vector equilibrium. The final lines, which are 1/4 the length of the edges of the original tetrahedron and the smallest vectors in the model, are thus designated as unit vectors. And you can see cool. Huh. You really can see the square there.
There's the cube octahedron inside of the dodecahedron, right? Rhombic. produce a rhombic cuboctahedron with the vector equilibrium.
Wow.
But do
And
you
then-
understand? You understand the principle that he used? It's always the repetition of the same thing
Yeah,
that the baby will
absolutely.
do.
That's
You
really
take an
important.
edge, you divide by 2. And you take each of the edges, you divide by 2. And you link to the closest. You take each edge, the bonding. That's why Becky always link it to bonding. You link to the closest. Remember, energy flows to the line of least resistance. That is, it bonds with what is the first closest to it. So if you divide and you have a point that are at the lowest, those are the relationship. The closest point. So you took the octahedron that is inside here. You took it. Each of the edges of the octahedron you divide by 2. So you have a midpoint. So how many midpoints do you have? How many?
Well, an easier way to do that is to start with your
Hold on, Richard,
triangle.
please. Hold on. You take the octahedron. If you take the midpoint, how many edges does an octahedron have? 12, isn't it?
12.
Right.
12 edges. If you take then those 12 edges, you section them in half. You mark a point, half, half, half. You have 12 points, right?
Right.
And you take each of those points and you link it to the closest. That's the way you build the cube octahedron in the tetrahedron.
Okay, let's
And that's
finish
the
this
only way it
page.
would fit in. I get, all right. Yeah. Okay.
No, go ahead. Go ahead.
No, I was just
Go.
thinking that by linking it to those closest points, that's the only way it would actually be able to kind
Yes.
of work out
Yes.
in the, yeah, okay. That makes sense.
Well,
You have the 12 edges of the cube octahedron and the 20 faces. Because
Right.
cube octahedron has 12 edges and 20 faces.
Yeah, that's what Richard was, yeah.
Yeah, that's what you obtain there. And the
Yeah.
vertices are those midpoints. Okay.
Right.
And I
And
see,
for me, another way of doing it is just on a piece of paper, even just draw a triangle and put points at the midpoint of the 3 edges and then connect those points. And your one triangle will turn into 4 triangles.
right.
And that gives you the basic sort of notion of multiplying by dividing. And you do it in a fractal sense, that you use the simple formula of always bisecting at the midpoint of the edge.
Yeah,
And then you just keep connecting the dots.
yeah,
And your one triangle will turn into 4, and it'll turn into whatever it is, 8 or 16, and it'll just keep on going and going and going infinitely.
But the cube octahedron hasn't got only triangles.
Well, I'm not talking about the cube octahedron. I'm just talking about the principle of multiplying by dividing, and the triangle is a simple way to sort of illustrate that.
yeah.
Yep.
Let's finish reading this last paragraph. 'Cause
All
that
right.
finishes the page before and then we're complete for the reading. I'll finish this off. We quickly run through the sequence in reverse to review the geometric relationships. A 4-frequency tetrahedron in which each edge is equivalent to 4 unit vectors is the smallest tetrahedron to contain a complete vector equilibrium in its center. And so it acts like an ultimate whole system, figure 1011, which is going to be on the next page, I think. The review starts in the center A unit length of 1/2 octahedron is tacked onto each square face of the nuclear vector equilibrium, thereby forming a two-frequency octahedron, which in turn has two-frequency tetrahedra added to 4 of its 8 faces to create the large tetrahedron, figure 1010. So here's figure 1010 right here. Figure 1010 illustrates this transition, and figure 1011 shows the complete 4-frequency tetrahedron and its implied archetypal hierarchical system, employing progressively thicker lines to emphasize the 3 different polyhedra. And here is that thing right there. And we're getting close to a tetragrammaton. It's starting to build. Okay, and that basically that leads us right up to this next section. So if we quit right here, any comments or questions about what we just read?
Okay.
Wrap
Can I
up.
comment?
Why don't you share your takeaways, how you're feeling, Manu, and share your takeaways and pass it along.
Okay. I feel good, like every Sunday morning. The purpose of the multiplication by division, or to demonstrate it, is to show how natural systems, pattern-like, can be divided into constituting a more complex system. That is a pattern. That is a cube octahedron. Remember that in the mind, the cube octahedron is expanded, whereas the tetrahedron is compact. So the compact, in its physical manifestation, is actually small, is stable. And the expanded, energy-wise, is a radiative. It is the divided. I'm through with what I want to say, is that you do this operation, multiplication by division, is for a purpose. And the purpose is to go from the most compacted system to the most expanded system and backward. And you can never tell that if you don't have anchor in your mind, that everything that presents itself is always with its dual. Although in our behavior, in the way we see and do things, we always ignore the role of a dual. You can't talk of a triangle without a rectangle or a square. You can't talk of the octahedron without a cube. You can't talk of the icosahedron without the cube octahedron. Those always go together. That's the biggest thing I take away from this. Otherwise, I wish you all and a perfect end of weekend and fantastic beginning of next week. Steve and our Canadian counterparts, and an excellent weekend. And myself, in between the two of you guys, I'm enjoying time. I'm enjoying the sunshine. So, Anne, how do you feel? What do you take away?
Yeah, I feel very entertained. Yeah, just but I can see a lot of the connections, right? Since the day we started, and this multiplication by division is making a whole lot more sense. And Richard, when you talk about that, using the triangle to show it, and I'm starting to talk about this in with my team as well. And I also started talking about the shape of space is another, which was very interesting. And then doing the cubes. No, what's that? We were doing multiplication using threes, right? Instead of the squares, using triangles instead of squares. But today, I don't know. I can see now what you mean by that the 12 gumdrops and then the toothpicks, right? So I just want to say that all of you should be thankful I'm not building anything, because when I thought of the gumdrops and the toothpicks, I have a dinner platter for dessert. Okay, so that's right there. But yeah, it was clear. That was what popped into my mind. Yeah. So thank you very much, everybody. And Joe, how do you feel, and what is your takeaway today?
You know, I'm actually taking away quite a bit. You know, a lot of the things that I've been looking into is self-referential systems, and I'm starting to see that how Bucky addresses these concepts through the ideas of synergy. And so you start to see the repeating patterns, and you start to see how he even gets to the concepts of, you know, kind of how these repeating patterns, these fractals, actually work towards simplicity and complexity. And there's an element of simplicity and complexity, and there's the micro and the macro that are directly related to that concept of how everything fits together. And what you know, I need to, there's something I need to do is spend a little bit more time with the geometrical aspects of it. There's no doubt in that, but I'm really starting to see what exactly you know, what Bucky was actually proving, and the reason he was doing it. And it was just, it's a, you know, it's really it's a new way of kind of looking at what it means to be conscious. So, or it's a way of restating it. And so it's, I'm going to be really interested in this in the next couple of weeks, because I've been thinking about this in a lot of different ways. But you know, these patterns and being able to spot these patterns and understand these patterns are actually directly related to what it means to be human. And it really has a really big impact on things like artificial intelligence. A really significant. And maybe one of these Saturdays/Sundays, I can actually demonstrate that. I'm pretty close on it. So, and it really is, it just becomes a lot more simple when you start to see and hear the discussion. So you know what, I think Anna had it right when, you know, yeah, it is entertained, but it's also, yeah, it's entertaining, but it's also, it's a privilege to listen to, because the more you listen to these concepts, the more clear they become. And so, you know, it's exciting. It's exciting. I mean, but I definitely have some work to do. I'm definitely over the next few days. So, Richard, how are you doing? What are you taking away from today?
Well, pretty good. And I guess I'm kind of stuck, I think, in terms of what became really important for me probably years ago now, in reading chaos theory and reading about fractals and the beauty of fractals in plants and whatnot. And the explanation was that that's just a simple formula that's repeated over and over and over again, and you turn this tiny little plant into something that's really beautiful in its pattern and makeup. And I finally understood this whole process through this particular sort of discussion of multiplying by dividing, and realizing a simple formula like mark at the midpoint and connect them and keep doing it over and over and over again, you go from something quite simple into something quite complex. Um, and you get there through a very simple formula that's just repeated and repeated and repeated. And it can go on infinitely. So what's helped me anyway is that if I think of the universe as finite, as we've been talking about it, and things can be infinite inside that finiteness, much like the figure 8, the symbol of infinity. And the figure 8 also is the figure of the butterfly in the butterfly effect. You see this beauty unfold through this simple little formula that says, mark at the midpoint, connect the lines, and do it repeatedly. That to me is my best understanding right now of how either simple gets to complex, or we've tried using the language of simplex, but how simplex also gets to complex through a simple formula. But anyway, I'm feeling good, and it's been very helpful to talk it out through a dialogue and keep coming to deeper and deeper understanding. Steve, Lee, how are you feeling, and what's your takeaway?
I'm feeling really well. I was very confused through almost a good half of the program. But I've got to admit, when you came up with your design that the child, the little boy, came up with in about a couple of minutes or whatever it was, after you took it home with him, that began to help me understand multiplication with division, or division with multiplication. Never thought about that. Ever. Like I said, I've raised two boys that are mathematicians, and my ex-husband is a mathematician, and I couldn't understand either one of them all their lives. And I'm now beginning to get it. I appreciate the book that was written for Amy. Amy wrote it for Fuller, and I am now very interested in reading Fuller's book. So I need to earn some money for that. And then also read maybe hers first, so that I can get more depth into what I learned. What have you taken out, or how are you feeling, and what have you taken out of this?
Well, thanks, Lee. I notice I'm feeling, one of my feelings that I'm feeling is frustration, because on the one hand, I really appreciate free-form learning and sharing. On the other hand, I'm charged with the idea of studying this book. And so, and I noticed that when we don't stay on reading the book and stay close to the book, I notice I have a sense of chaos, and that leads to some frustration. And I probably, if I understood what was going on in the book more, I'd feel more comfortable. So I'll do what I can about that. I have been, this whole idea of multiplication by division, I've said this before, this kind of awakening, a seedling of an idea that's coming into my brain, is that, and I've said it over before, that when if I have 3 apples three things and I multiply them by three things, how many things do I have? And I get more things. So when I think of multiplying, I usually think of having more. But in actuality, the way multiplication happens is one does not start with a thing and then magically, alchemically have more things. One must always start with a whole and divide to get to the things. If I want more apples, I don't multiply apples. I take a tree that grows apples and it has fractals of itself. And it divides itself and it grows. And so I've got this internal sensibility that all of my life I always thought about multiplying as getting more by and having a bigger and bigger volume. It never dawned on me that the only way to multiply is to start with a thing and divide it up so I have more of those things, which is blowing my mind. And I'm almost thinking that it's a language issue that, and I don't want to get, this could sound real political, but I mean, if I'm willing to talk about a sunrise and a sunset, when I'm willing to use language to maintain a trance of not seeing reality the way that it really is, I create amnesia in other parts of my life to where even though there are things that are dissonant and they don't make any sense because I live in a place of nonsense anyway, I tolerate nonsense. And when I start eliminating nonsense, when I start seeing sunset in the morning and sun clips in the evening, and seeing reality the way it is, suddenly I realize I don't get more apples by using a multiplication fiction of multiplying apples. A way I get more apples is I start with an apple tree and I use fractal division to get these little apple seeds that get apples that turn into apple seeds that grow more apple trees. In other words, all my life I've been starting with a thing to multiply instead of starting with a whole. And I think that's the big revelation for me, is that anything that does not start with a whole in the first place is a fiction that allows me to, if I'm a kid and I want more apples, I have to go get more apples. But if I understood that apples come from apple trees and I want more apples, I plant an apple tree. So if I'm a kid and I want more apples, suddenly I have to get political. I have to make friends. I have to go get apples and buy apples, or I get an apple tree and just grow the dadgum apples. And there's so much more self-sufficiency from the whole concept of multiplying by dividing. And the best way is Koch's snowflakes. The Koch snowflakes is the idea of fractals. I take a triangle and I take it in half and spread it out and make more triangles, and the whole gets bigger with fractalation. So I'm having this nebulous explosion going on in my head trying to understand multiplying. But what you holding up, Anne?
Yeah, I said drawing it out. I don't know whether you can see it.
If you take off the fuzz on your background, we can see it. You have a fuzzy back. Okay, that's it. Yeah, okay. You start with your triangle and you start dividing it up.
Yeah. So yeah, thank you very much, Richard.
Yeah, I start with the whole. I have to start with the whole in order to multiply. I can't start with a thing and expect it to magically multiply. And that makes me dependent on a system that gives me things instead of letting me see the nature of reality, which is things grow all by themselves. Anyway, I'm having this cognitive dissonance going on and understanding what's going on. So that's what's going on for me. And I'm complete.
Just connect back to what I started off with today, saying about the this presentation, and my struggle in Bohmian sense, where he talks about divided whole and undivided whole,
Yeah.
it starts to sound binary, so that you're eventually going to say one is better than the other,
Yeah.
and you want to stay in the both and. And Bohm talked about the Western science, analytical, if you want Western science, is really important. It has its place, but it's just got too big a canopy and it needs to make room for others. And so as I was trying to stay away from a binary of divided and undivided wholes, I realized that, all right, I could take an undivided whole, like the big whole that you're just talking about, and it can accommodate the divided whole. But I can't take the divided whole and bring the undivided inside it. So
'cause the
I have
divided
to
whole is
go
too
with
small.
what you just said. I have to go with the start with the whole and work my way to the parts, and not the other way around. Yeah.
Right.
Um,
There's
I-
a, go ahead, Anne.
Yeah, I just want to add something, which I will go into more details next week, because one of the things that kept running through my head when when the discussion was going on is, how do I get this to a 5-year-old, right? Because psychologically, children only at about the age of 16, they comprehend abstract concepts then, right? But below that, the abstract concepts are very difficult. Okay, but anyway, I'll come to that next week. But because of Mortensen math, I can see that's about right now the system that will accommodate, getting the kids the foundation to understand this. Because the one thing about Mortensen is you have to determine what one is. At any given time that you want to do any calculation, you have to determine what one is. So I'm gonna end with that, and then I'll take it further. As I figure out some of the things here, we'll talk about it next week. Yeah. Thank you so much.
I
Yeah,
like
sorry.
starting with one. I like starting with
Can I
one.
say
It's very
something?
good.
Yeah.
And there's a very simple method, very simple, to make it understand with little kids. You buy them a pair of scissors, a lot
No.
of paper, and glue, and scotch tape. And hold on. And you step by step build something with them.
Yeah.
Once a child does this, a child can do it. A 4-year-old can do it very well. You show it. Then they start, and you repeat, they start identifying with. And they grow with it as the basis of accounting. Remember, we always have a bias towards a system of doing something. That's what I would suggest you do.
No. Sorry, Manu. I will go further with it a little bit, because Mortensen, at 5 years old, the kids are already doing multiplication, division with big numbers. They're doing fractions, multiplying, dividing fractions. They're doing algebra, factorization, distance, area, volume. I will bring all that because for me, I'm figuring that and looking at what we're talking about today, these past months and years, from IVM to PSU to phi to golden ratio, etc. How do we lay the groundwork when they're 5 years old? So I'm looking at what Mortensen has done. So I'll talk about this, otherwise we'll extend the time. Okay.
But I don't think that you're getting what I'm saying.
I do.
Hold on. Do you teach a 4-year-old music?
Yeah. Yes, I do get what you're saying.
On. Yes. If you're teaching them music, they should know what the phi is. You can as well teach them what the phi is.
Exactly.
When
That's why
pressing a chord, is doing it. Okay. So
Yeah.
that's why I don't understand all the names, Mortensen and all this. Good for them.
Yeah.
But we have the tools within us in every context. We did adding by cutting trees, branches, and cutting them into pieces. Yes.
Manu, Anne's got a team that uses the Mortensen strategy as a foundation and basic, and so in order to teach these things, she has to relate to those things in order to do this. She can't start from anywhere in the universe. Go ahead.
No,
Go
she
ahead,
asked the question.
Good,
No.
and
How
No,
do
no,
you
no, I
teach
didn't, I
this
wasn't,
to
I'm not,
4
I'm not
years
asking
old?
a question.
Okay.
I'm not asking a question. It's
Yeah.
because for me, it's about doing what Mortensen has done, making all these very, very difficult concepts, and he's made it very possible for 5-year-olds to understand. So when I said how to, I want to use, come from that same thought, because he has done it, that we should be able to do it with all these other concepts, because they, to make it real and more concrete for children. Otherwise, we can't build upon it. Then we will do exactly what we've done right now in education, where they're giving the wrong foundation and building into something that we can't shift. It's very hard to shift from. So I mean, that's where I'm coming from. Okay, so we'll take that next week. Yeah.
Cool. Pick it up
yeah,
next
I'm
week.
really looking
Very
forward to
much
hearing
for
that.
getting me there. Yeah. All right.
Thanks so
Thanks,
much,
Ann.
everybody. Bye-bye.
Take care.